Hello, I'm Rajesh Bhaskaran from Cornell University, and here I'm going to show you a demonstration of running a complex simulation of fluid flow over wind turbine blades in Amazon Appstream. So you can run this complex simulation in a web browser using Amazon Appstream. And this particular example is taken from the wind energy course that mechanical and aerospace engineering students do at Cornell University, and so they design and build model wind turbine blades. This is 3D printed; it didn't come out right, so it became my prop. And they also test the amount of power they get in the wind tunnel. And there's another group of students who simulate this problem, and by solving the equations, they predict what kind of power you can get out of this particular device, and the idea is to compare the measurements to the simulation. And the equations are pretty complex. I wanted to show you, just to show you what they look like. And so here's one set of equations, that's conservation of mass, and this is basically F equal to ma, written for each little chunk of fluid. And you can't solve these equations unless you have the tool. In fact, I don't mean to scare you with those equations. And then I'll go to the Appstream, and if I switch windows here, so this is the tool we use, ANSYS, which is used by professionals. So you bring in the geometry and you put a boundary around the blades, and that's, you simulate the flow in the region between the boundary and the blade. And the first thing you need to do is divide the flow region into little chunks, and you do that through the mesh. So let me show you what that looks like. Okay, so and use some mathematical tricks to do just one blade. So this is 1/3 of a full kind of circular sector, and this is the outer region, and the blade is somewhere over here. In fact, if I go to the geometry, you can see, the blade is over here, and you have to go pretty far out to get good results, because you're assuming uniformity when you're that far out. And so that region you divide into little chunks, and you see the mesh. Okay, that's just the outer view, but you want to know what's happening inside. And for that, what you do is you use a section plane thing. So I'll enable it. I already have one. And using this section plane capability, you can basically cut through. Okay, so what I'm doing here is I'm cutting through this mesh. It has about 200,000 little chunks. The more the chunks, the more accurate your solution, because it's approximating the equations over each of those little chunks. And as you get closer to the blade, you want it to be, finer and finer, and that's somewhere close to the blade. So you have to examine this carefully, and I can't, I can't tell that this is running remotely. This is as good as the doing it, this level of interactivity, which is important, is as good as doing it on local machine, but it's running remotely. Okay. So I've divided my domain into little chunks, and then I need to, solve the equations over those little chunks, and that's done iteratively. And you go to the solver, and so I've already run the solution. And this is where, computational power is important. In meshing, the interactivity is important. Here, computational power is important. And I ran it using 2 processors, but this is where, as you divide it into more and, bigger and bigger number of chunks, more number of chunks, you want to have more computing power, and so you would run it over more cores. So through the Appstream, one could presumably get the amount of computer resources that you need, so you can run it on more cores, and that'll speed up the calculation. Okay, so at this point, I have a reasonable solution to my equations. So let's take a look at the results. That's the most exciting part. So this is the results viewer, and this just shows me, one blade. That's what we have approximated it to, and I can, reflect this 3 times and look at all 3 blades. And by the way, to make the problem tractable, you take the hub out. You can bring that in when you're doing a second iteration through and so on. But you want to approximate the problem in a clever fashion without losing the key physics behind it. So let me go back to a single blade, and then if I look at so I can take let's say I can take a section through that and see what the flow is doing. Okay, again, it's like I'm releasing flow particles here, and I can see how it's flowing over the blade. I can also look at vectors of the velocity. So this is proportional to where I have longer vectors, the flow is faster, and where I have shorter vectors, the flow is slower. And here, if you look carefully, you see that the flow is going around. That's not good. You're losing power. So this needs to be redesigned in order to minimize that. And what else can I show you? You can also look at the pressure on the blade. And this is where you see these, it should be smooth, and you see these jaggedness because there's a problem with the way the CAD is done. And again, the student needs to, in this case, need to go back and fix how the geometry is created. So you have to, use engineering judgment to evaluate the results, and that's a great teaching opportunity. And then you can take a section through here and see how, so you can see there is higher pressure here and lower pressure behind, and it's that pressure differential that'll cause a force. There'll be a force component that'll cause it to rotate, and that's proportional to the power. So you can get all these interesting results, and if you can run it in a web browser, then we can it doesn't have to be an expert. Any engineering student should be able to run these kinds of complex simulations and really build intuition about how you design these devices to get maximum power out of it. Hope you enjoyed this demo.